Now to the results themselves. So we start with this lemma. Let's just read it and see what it says. Lemma 1. Let x, gamma, f, beta satisfy assumption 2. These are the givens in the problem, see? So the set of states, feasibility correspondence, return function, discount factor, okay? Once you have these, you can define the problem of maximizing discounted present value subject to feasible plans, okay? So suppose these satisfy assumption 2, then for all starting states x naught and all feasible states x tilde that start from x naught, the following relationship is true. U of x tilde is equal to f of x naught x1 plus beta u of x tilde prime, where x tilde prime is x1, x2, blah, 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 blah. Okay, so what is being said? We can read it in several ways. So x tilde is any feasible plan starting at whatever, x2, x3, starting at x naught. And then when I look at that plan starting at x1, the same plan, I'm going to call that x tilde prime, okay? So what is being said is that the discounted present value that I get from this feasible plan, is equal to the 0th period or the current reward from the plan plus beta times u of x tilde prime. So I want to know what u of x tilde prime is, right? So one way to interpret this is that u of x tilde prime, and this is absolutely right, that u of x tilde prime is the discounted present value from tomorrow onwards of the plan, the remainder of the plan, right? And when put that way, it seems to make eminent sense, right? But I also want to write u of x tilde prime explicitly in notation. And when I write that, I want to keep in mind that this u function has to do with discounted, u has to do with discounted present values from t equals 0, right? Starting at 0. Whereas, this starts at 1. The point is it doesn't matter. So if I write it here, it should look something like I'm starting at t equals 0, going all the way to infinity, discounting by beta to the t, right? And my current rewards in period t. So now I have to be a little bit careful because this plan here is this one, right? So it's starting at the initial state x1, okay? So when I write my, if I were to write xt comma xt plus 1 in there, right? then at t equals 0, I have x naught, x1, but that's not what this is all about, right? So the first current reward should be x1 comma x2 because it's starting with x1, right? So how do I do that? I do that by a sleight of hand. I write here xt plus 1 comma xt plus 2. Nothing has changed. Everything starts at time 0 now. The only thing is that the path starts at x1, x2. At t equals 0, this is x1, x2. At t equals 1, it will be x2, x3, etc., etc. Okay? It's really another way of saying that, look, after time 0, I've arrived at time 1, but now when I stare into the infinite horizon, what do I have? It's like I'm at time 0, but the initial state is x1. Okay? And I'm doing this summation. Right? Okay. So formally, why does this hold? So formally, u of x tilde, which is this, right, is this limit of partial sums. Okay, this limit of partial sums. So let me take the limit out and let me, instead of skipping any steps here, let me do the following. So let me say that this is equal to limit n tending to infinity of this finite sum here, this nice and finite sum here. So what is that nice and finite sum? It's f of x naught comma x1 plus what? So then what do I have? So I have this. What has happened at t equals 0 is I've received f of x naught x1, right? So then I've incremented t to t equals 1, okay? So what remains must be all the terms, sorry, n, all the terms here starting with t equals 1, right? So all the beta to the t f of xt t plus 1 term starting with t equals 1, right? So that is what we have. So what I want to do is, so I want to take limits, right? So when I take limits, this horizon becomes infinite. When this horizon becomes infinite, I just get another series, and it's no big deal to change it to a series starting from 0 to infinity. We've done this earlier. Let me do it one more time, right? So instead of doing it directly, let me do the following. Let me say that instead of this, I want a summation that starts not at 1, but at 0. Okay, so let me change the index. Change index from t to s as follows. So let t be s plus 1. Okay, and then what will happen is that when t is equal to 1, s is equal to 0. Okay, if I have a 0 here, t is equal to 1. So in terms of s, I can write this summation as summation s going from 0, so when t is 1, s is 0. When t is n, s is n plus 1. See? So if I have t is equal to n, I want n is equal to s plus 1. So s must be n minus 1. N minus 1. Okay? So t equals 0, sorry, t equals 1 implies s is equal to 0, t equals n implies s is equal to n minus 1. Okay, and then beta to the t, so instead of t I'm using s plus 1. F of xt, so x s plus 1, x s plus 2. All right? If you want, you can put the t back here, or you can just retain the s. So what I have is that this whole thing here is equal to limit as n tends to infinity of f of x naught x1 plus summation s going from 0 to n minus 1 beta to the s plus 1 f of that, right? So that is f of x naught x1 plus I bring out one of the betas, so beta to the s. So now you can see that this thing here, right? It's just a partial sum of discounted present values of the original problem that starts at t equals 0 or s equals 0. Yeah, the only difference is that it'll start at s equals 0, but the first state will be x0 plus 1. First state will be x1. Okay, so what is being said is that if I now take the limit of this as n tends to infinity, as n tends to infinity, n minus 1 tends to infinity. Okay, yeah, if I take this limit, that is exactly the discounted present value to me of a problem starting at time t equals 0 or s equals 0, but starting at the state x1. Okay, so I plug that in here and I have the right hand side. So once again, what is this lemma? It's saying take any feasible plan, then it must be true that the discounted present value from this feasible plan starting at t equals 0 is equal to the sum of the t equals 0 current reward plus beta times the discounted present value of the rewards starting from t equals 1. That's all. Okay, the only thing why we've sort of replaced the t equals 1 with the t equals 0 is because the u that is defined here, the discounted present value of the series, that's defined over sums from t equals 0. Okay, and the reason it doesn't matter is because whether you start from t equals 0 or t equals 1, because you're going into the infinite horizon, that's what counts. Okay, and you can see from this argument, this equivalence argument. So theorem 2 says that suppose the state space or set of states, feasibility correspondence, return function, and beta satisfy that the feasibility correspondence is non-empty and that the series, that's the limit of partial sums, exists. That's all. Assumptions 1 and 2. Then V star, which is the value function to the sequences problem, is a solution to the Bellman equation or the functional equation. Okay. So this is what we showed when we removed the soup and we had maxes and we just maxed, we reduced our max problem by cutting it into two, that we first max from x2 onwards and then we max over x1. Okay, so we're going to do something similar here, although it's sort of it may seem a little bit hidden. Okay, fine. So what do we start with? We start with that V star of x naught is the soup over the discounted present values over all feasible paths starting at x naught. Okay, so given this, show that V star satisfies Bellman's equation. So show V star of x naught is equal to soup. So here the next period's choice is being called x1 rather than y. The reason is that we're going to use this sequence in which we call stuff x0, x1, x2, etc. So soup we want to show this. Okay, so first we want to show this in the case where V star of x naught is finite. Okay, so where V star of x naught is finite, we want to show that V star of x naught will satisfy these two sets of inequalities. The first, that V star of x naught will be greater than or equal to this right hand side, f of x naught x1 plus beta V star of x1 for all x1. Okay, so that's a property of the soup. So soup of this must be greater than or equal to anything that I put here with any x1. That's the first thing that I want to show. And the second thing is, given any epsilon greater than 0, I can find some x1 here such that this is so close to V star of x naught that V star of x naught is less than or equal to f of x naught x1 plus beta V star of x1 plus epsilon. Okay, so first we show 4. So what do we use to show 4? We use the following, that for the sequences problem, V star of x naught is greater than or equal to the discounted present value u of x tilde from any feasible plan. Okay, so start with that. Then lemma 1 says I can write u of x tilde as current returns plus beta times u of x tilde prime, where x tilde prime is the path, the feasible plan starting with x1. Okay, right. So V star of x naught is greater than or equal to all of these, and any of these can be broken up into current reward plus beta times the future discounted present value. Okay, all right. What do we want to show here? So remember, what we want to show is v star of x naught is greater than or equal to. So let me write this out. So v star of x naught is greater than or equal to, that is equal to this. Okay, and what we wanted to show was v star of x naught is greater than or equal to f of x naught x1 plus beta times v star of x1. Okay, that's what we wanted to show for any x1. Yeah. Then it would show that v star of x naught is the soup of all these. Okay, so what we want to be able to do is just replace this u of x tilde prime by v star of x1 without disturbing this inequality. Right, so how do we do that? We do that by noting that starting at x1, since v star of x1 is equal to soup u of x tilde prime over all x tilde prime starting at x1, right? It must be the case that, so since this is true, we have that for all epsilon, I can find x tilde prime such that u of x tilde prime is very, very close to v star of x1. Okay, v star of x1 adheres to the set of all the u of x tilde primes. Yeah. In fact, u of x tilde prime is greater than v star of x1 minus epsilon. Okay. So if this is true, then this thing here is greater than or equal to, if you wish. I'm now replacing u of x tilde prime with v star of x1 minus epsilon. So I have a minus beta epsilon. Okay. So v star of x naught is greater than or equal to f of x naught x1 plus beta v star of x1 minus beta epsilon. And this is true for any epsilon greater than or equal to 0. So this inequality is going to hold. Okay. So that is your inequality 4. Okay. So to show that v star of x naught is the soup over all these, first you must show that v star of x naught is greater than or equal to all of these over all feasible x1. That is done. Yeah. The next thing you have to show is that if you have any epsilon, no matter how small, you can find an x1 such that this will be so close to this that when you add epsilon to this, it will be greater than or equal to v star of x naught. Okay. So you use the corresponding inequality for the sequences problem, that v star of x naught is the soup for the sequences problem. It's a finite soup in this part of the proof. And so for every epsilon, you can find a feasible plan such that the discounted present value from the feasible plan is so close to the soup that when you add epsilon to it, this becomes greater than or equal to v star of x naught. So you start here, right? Once you start here, you then unpack this. You say, hey, this is the current reward plus beta times discounted present value from tomorrow. Okay. And then you say, look, this is discounted present value from tomorrow for this feasible plan that I had. That feasible plan is something where the original discounted present value is very, very close to V star of X naught. But no matter, it's a feasible plan, okay? So for this feasible plan, it must be that the discounted present value from tomorrow, which basically starts with state X1, must be less than or equal to the best that you can do, the soup, which is V star of X1. So this is less than or equal to that, and so that is less than or equal to this. Okay, that's your inequality 5. And so 4 and 5 together give you that V star of X naught is in fact the soup of f of X naught X1 plus beta V star of X1, overall feasible X1. Okay. So let's quickly also look at what happens if V star of X naught is not finite. Okay. Suppose V star of X naught is positive infinity. What you want to show is that there's a sequence of these next period states that you can choose feasibly, x1k's, such that the limit of this goes to infinity. That's why the soup is infinity. That's what you want to show. Right? So you start with noting that V star of X naught to start with is the soup for the sequences problem, and it's infinity, which means that there's a sequence of plans, infinite sequence of plans, okay? And this sequence has the property that the discounted present values over this sequence, as you take k to infinity, goes to infinity. That's why the soup is infinity, right? But for any of these, you can unpack any of these for any plan k. So for each k and x tilde k being a complete plan that starts with x naught, goes to x1k, x2k, x3k, so forth. Okay, so for each k and x tilde k, you have that this discounted present value is the current reward plus beta times discounted present value from tomorrow. And the discounted present value from tomorrow necessarily is less than or equal to the best that it can be, which is V star starting with x1k. Okay, so what do we have? We have u of xk less than or equal to okay. Now take limits as k tends to infinity. Okay, so we had a sequence of plans so that in the limit the discounted present value went to infinity. So this goes to infinity and therefore this goes to infinity. So you've shown that V star of x naught is infinity, but then there's a sequence of next period states such that this right hand side of Bellman goes to infinity. Okay. Finally, suppose V star of x naught is negative infinity. Then you want to show that no matter what state you choose tomorrow, you will get negative infinity on the right hand side of Bellman as well. Okay. So left hand side and right hand side of Bellman will be the same. So you start with what you know about the sequences problem. If v star of x naught is negative infinity, that means that for any feasible plan, the discounted present value is negative infinity, right? So now for any of those plans, the discounted present value can be written as current reward plus beta times discounted present value from tomorrow. This is always a real number. Okay, so this negative infinity means that this is also negative infinity. But if this is negative infinity for every plan starting tomorrow, then the best you can do starting tomorrow is v star of x1 is negative infinity. But if the best that you can do tomorrow is negative infinity, then that plus whatever the current reward is negative infinity. Okay, so that's it. So now I think there's a time constraint here because I'm operating from home. So what I'll do is I'll return to theorem 3 after a break.